In this lecture, we'll start a new chapter and we'll learn about functions. This is chapter 6 of our first textbook, Fundamentals of Python. In this lecture, we are going to talk about functions which are useful in structuring code in a program. We also learn about a recursive function, how we can define them. We also briefly discuss higher order functions for mapping. A function packages an algorithm in a chunk of code that you can call by name. So we assign a name to each function. There might be input arguments. It's optional. And we run the function and we get a result. So a function can be called from anywhere in a program's code, including code within other functions. It means that we can call a function under another function procedure. A function can receive data from its caller via argument, but it is optional. It means that we can have functions which do not need any input arguments. When a function is called, any expression supplied as arguments are first evaluated. So we need to receive input arguments first, and then execute the rest of the code. A function may have one or more return statements. So if we want to see the results, we need to have a return statement. Otherwise, it runs the code, but we are not able to see the results. You are going to see in a few examples. So a function may have one or more return statements. Overall, functions support the division of labor like organizational charts. In a well-organized system, each part does its own job in collaborating to achieve a common goal. So there is a common goal, then there are several parts working together to achieve that goal. In a computer program, functions can enforce a division of labor. What does it mean? It means that each function should perform a single coherent task. For example, there might be a function which computes a summation. So it's clear the goal and the purpose for that function. Each of the tasks required by a system can be assigned to a function, including the task of managing or coordinating the use of other functions. So the best example here is the organizational chart. This is the top level. Then we have several subdivisions, and under each there might be several other divisions. So here, this division, if this is D1, D2, Division 3, Division 4, and Division 5. Okay. So Division 2 pass on inputs to both Division 4 and 5. So it means that to run the function for Division 5, for example, we need some inputs from the upper level. So functions can work together, and eventually Division 1, this function can pull things together and then return the result to the program. It's the same concept for functions. Now, the syntax of functions in Python. Definition of function consists of header and body, just like loops. We use def. It's a reserved word, so its color is green. And then the function name, it's arbitrary, whatever you want to call your function. And then input parameters. Here you see a very simple example that calculates the square of a number. So we define our function, a square. There is just one input argument, and then it returns x times x. So let's run this and see what it looks like in Notebook. So whenever we want to define a function, we start with def or define, then the name, pay attention to color, and then X, input arguments, and then colon. In order to see the results, we use the return statement, and then X times X. When you run this code, you don't get any error, but you don't see any results. So you need to call function and pass on input argument. So a square, let's say 3. And then we see 3 raised to 2. So 3 times 3 is 9. We can try 10. And you run it, and then you see 100. So this is the very first function we just defined. If a function contains no return statement, Python transfer control to the caller after the last statement and the function's body is executed. So there's going to be a special value. The special value none is automatically returned. So if we really want to see the result, like 2 times 2 equal to 4, then we need to use return. Otherwise, the special value none is returned. Functions serve as abstraction mechanisms by eliminating redundant or repetition code. So when we want to write our code, always need to have a plan. So we decompose the problem. For each sub-problem, we may define a function. The purpose is clear, and then at some point we pull things together. So it helps with the abstraction mechanisms, and also it structures our code so we can communicate with the user or other programmers clearly. So in this slide, you see an example. We define a function summation, which calculates the summation from lower through upper. We initialize a variable here, result, and then you see a while loop. While, and this is the conditions here. Lower, as long as lower is equal or less than upper, do this. Augmented statement, result equal to result plus lower, and then add 1 to lower, go back to the while loop. If the condition is met, do this again. After you are done with the while loop, then return the result. So let's try implement this piece of code. So define summation. We need 2 input arguments, lower and upper, colon, result equal to 0, and then we have a while loop. While lower is equal or less than or equal upper, then colon, result, augmented statement, assignment, lower, and then update the value for lower by 1. And then if we want to see the result, return a statement, and then you run this. Okay. Now let's test our function with 2 inputs. Let's say 1 and 4. So 1 plus 2 plus 3 plus 4. The result is 10. We can test it with other numbers, 100 and 1,000. Then this is the result. Okay. So the summation of numbers 1 through 4, 50 through 100, and you can see a couple of examples here. Now, there are different design strategies for your code. One of the most commonly used is a top-down strategy. In top-down design, you decompose a complex problem in a set of simpler problems and solve this with different functions. So we assign a function to subproblems. In some cases, you can decompose a complex problem into smaller problems of the same form. Okay. Then subproblems can be solved using the same function. So you have decomposed the problem, and for each, you are using the same function. It's doable. But this is the special case of function. Then this design strategy is called recursive design. Resulting functions are called recursive function. It means that these functions call themselves over and over until we meet the termination condition. So a recursive function is a function that calls itself, and to prevent function from repeating itself indefinitely, it must contain at least one selection statement, because we need to check that condition, and based on that, we can decide whether to stop or to continue the program. So there is a risk here. When you go with the recursive function, we should be careful about indefinite iterations. Here you can see an example. Display range. So we have, for display range, this function outputs the numbers from lower through upper. Okay. We also have a while loop because we want to go through all numbers. We print them and then we update the lower number, and we do this as long as lower is less than or equal to upper. It's an iterative process. We can do it with while loop. But also, based on the definition of recursive function, we can use a recursive function because the recursive function can be used for iterative processes as well. So let's try to implement this with while loop, okay, and see what the results look like. So I define a function, we name it display range. Lower and upper are two input arguments, colon. So we have a while loop. Lower less than or equal upper, then colon. Print that number. Update the value for lower. And this is our function. Now let's call this function and try 1 through 5 as input parameters. So you can see that it prints numbers from lower through upper, 1, 2, 3, 4, 5. So for this function, we just use a while loop. Now we want to see how we can convert this function to a recursive function. We can replace loop with a selection statement and assignment with a recursive call. So we have the same function here. Now we add a selection statement if lower is equal or less than upper, print that number. And then we call the function. So display range, but we update input parameters. So we add 1 to lower, upper remains the same. So when it calls this function, it goes back to the top and then checks this condition and prints the result. Update the input argument and then goes back to the top until this condition holds. So it continues this process. So let's implement this. So we are making the same function with while loop a recursive function. So define display range, lower, upper, and if lower is less than or equal to upper, then call the function. If we don't call the function, then it's not a recursive function. So display range, update the value, lower +1, upper remains the same. Oops, here, first we print the number, and then we call. Okay, let's run this. Display range. We try it for 1 and 6. So it prints number from 1 through 6. So these are like two different strategies to write the same function. This one is a recursive function. This one is just a regular function that we used well to handle the iterative process. Most recursive functions expect at least one argument because you need to update that argument and then recall the function. So remember this. Here you can see another example, recursive version of summation. So we had this example in the beginning. So we defined a function called summation, which add up numbers from lower to all the way through upper. Now we can make it a recursive function. We have this selection statement. If lower is greater than upper, return 0. Else, return that number plus the summation. So here we call the function again, but we update the first argument, lower +1, then upper. So let's run this in a notebook. So we have define. So this is the regular version of this function. We use the while loop. We updated variables. Now we want to make it a recursive function. Define summation, lower, upper, colon, the selection statement. If lower is larger than upper, then return 0. Else, return lower plus summation. We call the function, we update the first input, lower +1, and then upper. Okay. Now let's test this with a few input parameters. Summation 1 through 4, it's 10. We got the same results before. You can try 100 and 1000, and it would be the same number here. Just two different ways to code the same problem. So here's another popular example for recursive function. You might be familiar with Fibonacci sequence. It's starting from 1, and each number is the sum of two preceding ones. So 1, 1, these two is the summation of 1 plus 1. 3 is the summation of 2 plus 1, and so on. So fib of n is equal to 1 when n is equal to 1 or 2, the first two numbers. And fib of n is equal to fib of n minus 1 plus fib of n minus 2. So this is a classical example for recursive function. We call the same function 2 times. Okay. And here you can see the definition of the function, the recursive version. So we define fib of n, which returns the nth Fibonacci number, and then you can see it's very simple. If n is less than 3, technically the first condition, we return 1. Otherwise, we call the function twice, and we update the input parameter. And this function only needs one input argument. Okay, so let's quickly implement this here. So So we define fib of n which returns the nth Fibonacci number. If n is less than 3, return 1. Else, return, call the function n minus 1 plus fib of n minus 2. Okay. To see the result for our function, we need to test it with a few numbers. So fib of 2, we expect 1, so it returns 1. Fib of 3, we expect 2. Fib of 10, 55. Fib of 100. And pay attention to the computational time here. So you can see the circle, it means the kernel is busy. And see how long it takes to calculate fib of 100. I'm going to interrupt the process and now test fib of 50. You can see that it is still taking time. So keep this in mind for recursive functions, and we are going to discuss it in our next lecture when we talk about computational complexity and overall recursive functions. So you can see that I still don't see the result for fib of 50, but when I want to calculate fib of 10, it's pretty quick, less than a few seconds, but this one is still running and I cannot see the result. Let me interrupt this and then try for 25. It's pretty quick. Let's try 40. You can see that now it's taking more time. So we will talk about the computational time and complexity with focus on recursive function later on. But you can see that for different input parameter, the computational time would be different. So stay tuned on this. Okay. Infinite recursion. Infinite recursion arises when programmer fails to specify base case or to reduce size of problem in a way that terminates the recursive process. So we need to have the right termination condition, either by defining a base case or reducing size of problem. Otherwise, we run into indefinite recursion. And here's an example. I define a function and I call it run forever. There is just one input argument n, and if n is larger than 0, then call the same function run forever with the same input parameter n. So it's always running run forever of n. Otherwise, then run this n minus 1. And let's see what happens when we run this. So define run forever, one input parameter if n is larger than 0, colon, we call the function run forever with the same input n. Else, call the function again forever, this time n minus 1. Okay. So I call this function run forever. Let's just try 1. So you can see that it's running. Look at this circle here, and then you get this recursion error. Maximum recursion depth exceeded in comparison. because this condition is always true. Run forever 1, then it calls the function over and over, and there is no condition to stop. So when you use the recursive function, be careful about this part. Functions as data objects. Functions can be assigned to variables, passed as arguments, returned as the values of other function, and stored in data structure. We can have a list which represent different functions. So here you can see several examples. ABS, we worked with this function before under math module, which returns the absolute value. So when ABS, it's a reserved word, so its color is green. When you run this, you get this result. Function ABS needs 1 input argument. Now math.sqrt, which calculates the square root of a number. Now we can define a variable f equal to ABS. Now f becomes an alias for absolute value. And then I can call f. Let's see what it looks like. So here f equal to ABS. Okay, we assign it to a variable. Now you get the same result. Now f is a function which represents ABS, so just an alias for that function. Now, if we want to apply to function to that argument, like this example, f of minus 4, then we expect to see 4. So f of minus 4, the result, f of minus 10, 10. So it's working. We can also have a list. Let's say we define a variable, funcs, and it's a list because we are saying square brackets, and we put the function in that list. So this list has 2 items, absolute value and the square root of a variable. So to get access to this these functions, we need to specify their position. So in a list, each item is assigned a position or index. The first one index is 0, the second item is 1. So first I need to specify the index or the position of that function in a list. So funcs 1, so 0, 1, it means that now use this function and then pass on the input argument. So the square root of 2, and then you get the result. So let's try to implement this. So I'm defining a variable, which is a list, and it has 2 items, 2 functions, and then math.sqrt. I also import the math module first. I run this. So you can see that functions are like an object. Now I want to apply the second function, math.sqrt to 4, for example. So I call my variable funcs, its position 1, and then the input argument 4. So we expect to see 2. We can try it with 3, and then this is the square root of 3. So we usually use this technique when we want to use several built-in functions over and over. So we define a variable and we put the commonly used functions in that list, and then we call them. So that's how you can use function as data objects. Now a little bit about higher order functions and mapping. Mapping applies a function to each value in a sequence and returns a new sequence of the result. So if we are working with lists as our data structure and we want to apply a function to each item, then we need to write a for loop, right? We need to go through all items, apply that function to those items. But if we use the map function, we can apply that function to all items in a list. And here's an example. A list named words that contain a string that represent integers. So there are integers, but their data structure is a string. So if we want to add them up, we need to convert them to numbers. If we want to replace each string with corresponding integer value, we use the map function. So map, and then the first input argument, what function you want to apply. Here we want to make them integer. So we apply the int function and which variable, words. So let's try to implement this. So I have a list called words, a square bracket, a sequence of strings, 2, 3, 1, 20, minus 45, and then 99. Then I use the map function. I want to convert them all to integers, so int words. This is a function, so you see this. Let's look at our variable. So you can see that it's still a strings. So the original list isn't changed. Now to reset variable, to change it, we apply the list function. Okay. So I call my variable words. List makes everything a list, and then I apply this map. Integer applied to words. We run this. Now if you print words, you can see that these are now numbers. They're all integers. Now we can add them up. So if we want to apply a function to each item in a list, we can use the map function, which makes things easier. Otherwise, we need to write a for loop to get access to each item first and then change their structure or apply another function to that. So in summary, in this lecture, we learned about functions. We discussed a specific functions called recursive function, which calls itself. There are two parts, base case and recursive step, and overall can be computationally expensive. So we tried Fibonacci of n, and we saw that if we increase n, then the computational time increases as well. We also discussed higher order functions, which expect other functions as arguments and return functions as values, like map. And a mapping function expects a function and a list of values as arguments.